Alright, welcome back everybody. In this video we're going to look at specifically lifting work or pushing work. Work done, in moving some object. The opening narrative talks about work being done. Work is force times displacement, and we'll look at two fairly simple and uninteresting examples here. Find the work required to push a box 10 feet if it requires 30 pounds of force to push the box. So our work is just going to be force, which is 30, times displacement, which is 10, and the work done here would be 300 foot-pounds of work. Alright, similarly, find the work required to lift a box 2 meters if it requires 40 newtons of force to lift the box. So again, work equals force times displacement. And so this is going to be 80 Newton meters of work required to lift that box. Alright, that's simple and not very interesting. Now, when the amount of force varies as we do work, then it becomes a little bit more interesting. We're going to find the work required on a variable force situation by using the integral from one end of the location of the object to the other of the force that's required, and we'll also apply this where force is applied vertically, and this is going to lead to some nifty problems. Let's look at example 3 again. This one's not terribly interesting, a little bit more interesting than the first two. Find the work required to move an object from position x equals 0 feet to x equals 3 feet if the force that is used is modeled by this function. This is a straightforward integral calculation. We want the integral from 0 to 3 of the force. And I'm just going to go ahead and punch that up. You'll take the integral of 50 minus e to the x with respect to x, 0 to 3. And we get that the force is 130.914, and since our units are feet and pounds, that's going to be foot-pounds of work. Alright, let's look at example 4. A leaky 5-pound bucket is lifted from the ground into the air by a worker pulling in 20 feet of rope at a constant speed. The rope weighs 0.08 pounds per foot. The bucket starts with 2 gallons of water, which weighs 16 pounds, and leaks at a constant rate. It finishes draining just as it reaches the top. How much work was spent doing each of the following? And you're going to have a very frustrated worker here who's lifting the bucket, and by the time it gets to the top, it's completely empty. But nonetheless, let's take a look at the actual calculations behind finding the work. First thing we'll look at is lifting just the bucket. Okay, now the bucket doesn't change weight at all while we're lifting it. So this is going to be a very straightforward calculation. The work required is based off the force. The force required to move the bucket is based off of its weight. So the force is going to be 5 pounds. And the distance that the bucket is being moved is 20 feet. And so the work required to lift just the bucket alone is going to be 100 foot-pounds. Now's where it gets interesting. Lifting just the rope. Now when we first start lifting the rope, we have 20 feet of rope to lift. But by the time we're done lifting the rope, we have no feet of rope left. So the force varies as we, begin, from the time we begin to the time we end. And so we're going to kind of define this coordinate system where we'll have 2 coordinates, the amount of rope lifted and the force required. And I can set up 2 points. When no rope has been lifted, the amount of force required to lift the rope is 1.6 pounds, 0.08 pounds per foot times the 20 feet of rope. Once you've lifted all 20 feet of rope, there's no force required because you're done lifting the rope. And this allows us to establish an equation for the amount of force required to lift just the rope. And so the slope of these 2 points, and this should come as no surprise to you if you're thinking about what the situation is, the slope of this is going to be negative 0.08, which is exactly the amount of weight that you lose for every foot that you lift the rope. And so our force function for lifting the rope is going to be negative 0.08x plus the initial weight of the rope, 1.6. And in order to find the work required, we're going to integrate this over the entire distance that the rope was lifted. And that will give us the amount of work required to lift that rope. So I'm going to go and integrate this to 0.08x plus 1.6 with respect to x, 0 to 20. And again, this is one I could certainly integrate by hand. I'm just opting not to. It's going to take 16 foot-pounds of work in order to lift just the rope. Then we consider the water, and we're going to do something very similar in there, and we're going to look at the force required and the distance that we've lifted the water. So distance and force, and we're going to look at 2 different coordinate points to set up our function. When we've lifted the water 0 feet, the bucket is full, and so it has 16 pounds of water in it at that time. Once we've lifted the bucket the entire 20 feet, there's no more water left in it, so the weight of the water is 0. We find the slope in this situation and so the slope of this function is going to be negative 0.8. And so the force required to lift the water is negative 0.8x plus 16. And so we're going to integrate that from 0 to 20. Because of the similarity of this and the previous function, I could definitely find this value of the integral without doing any work. Or I should say any calculation. I'm not really doing any work when I'm typing into my calculator. And we get that it requires 160 foot-pounds to lift just the water. And so the total amount of water, which we're going to find in part D, of lifting the water, the bucket, and the rope, we're just going to take each of these individual works and add them together. And so the total amount of work required to lift the water, the bucket, and the rope is going to be 276 foot-pounds. All right, that's the end of this lesson on lifting work. We're going to come back next time and look at Hooke's law and some applications related to that. Okay, see you next time. Have a great rest of your day.